So for those of you who just entered, this is the Big Ideas in UV LED session. Our next speaker is Mike Higgins from Illuminating Technology, and he's gonna speak about, or his topic is Illuminate Production Dark Spots with LED.
Thanks, Jennifer. Good morning, everyone. My name is Mike Higgins. I am with Illuminating Technology. Illuminating is now a brand of Excelitas Technologies. We are really excited about combining these two companies who have been involved in manufacturing UV LED systems for several decades. So adding the folks from Excelitas and the folks from Illuminating in the room together, we believe is really going to yield some great advancements for the UV industry. We're all very committed to UV, specifically to UV LED, and looking forward to what comes from all of it. I've been with Illuminating for 10 years. Prior to that, I was with Sardimer for about 10 years as well, which somehow adds up to a total of 20 years in this industry. I'm sure you've all gone through some of that kind of realization over your years in your industries, and always excited to be here and part of RadTech. So what is this Illuminating Dark Spots presentation all about? I'm going to talk in the beginning just a little bit about some of the key benefits to LED and how they can really improve your manufacturing process and your overall throughput. I'm going to give you 4 real-world examples of how UV LED was able to solve some sort of production problem or bottleneck and increase throughput and productivity. We're going to talk a bit about sustainability. There's some really good numbers associated with sustainability and UV LED. And that's a big buzzword. It affects everybody these days, so it's an important factor for everyone to consider with manufacturing technologies. And finally, what questions should you be asking your customer base? What questions should you be asking to uncover what some of the challenges are that they face day to day, and determining whether or not LED may be a solution that could be inserted into that process. There are a lot of different end uses, a lot of different markets for UV technology. We kind of lump them into a few different categories. Printing or graphic arts encompasses everything from digital, flexo, screen, offset. You've got coatings, which is this big area, and you've got adhesives. In each one of these segments, you've got folks that are going from traditional UV, mercury, arc lamp or microwave technology to UV LED, and that's one transition. That's kind of straightforward. The chemistry is different, but it's not wildly different. It's UV curing. The operators are used to how UV works, and the transition, for the most part, can be fairly straightforward. When you're going, particularly in coatings, and to a lesser extent adhesives, you're going, companies are going from a thermal cured process to a UV LED process, and that's a bigger change. So there are larger barriers to kind of cross when it comes to transitioning from thermal cured to UV LED. However, the reward, the pot of gold at the end of that rainbow is really, really big, because now you're going from typically kind of a slow, a very energy consuming process to something that's instant. And it's really fascinating to see people who see UV for the first time and it actually works, and they scrape it and thumb and wow, oh my goodness, it's completely cured. One area that all of these applications can benefit from is more energy density, or dose. And dose, it really comes from the number of diodes, the way that they're arranged on an SLM or a wafer, and the amount of that energy that you can get onto the surface of the liquid chemistry. So what are some of the benefits to LED? Well, the one that does seem to come up very often is the consistency of output over time. The wavelength in the high UVA range is not going to change or shift at all over time. You'll have a slow degradation of the picoradiance output of the unit over time, but that can be compensated for in a few different ways. Really, the consistency of the wavelength output over time means that the reaction is going to be consistent day in and day out for several years. We expect systems to last at minimum 5+ years. For years, we talked about thousands of hours, 20,000, 50,000, 100,000. It all depends on your working environment. If you keep the units in a safe, good, clean environment, they're going to last several years. And ideally, they outlast the machine that they're on. Another major benefit to UV LED is the footprint. The physical footprint of a UV LED curing system is significantly smaller than a traditional UV system or of a thermal cure, kind of a bake process. Space nowadays is more expensive than it's ever been. The cost to expand your manufacturing facility is significantly higher than it was just a couple years ago. And all of these factors, play into decision-making for companies. So instead of expanding your space to add more footprint, what if you could reduce the footprint of your existing manufacturing process? That really gets the attention of upper management at companies. And they start to think about more of a conservation thought process versus just an expansion thought process. Similar, Southern California has got a lack of water. We deal with droughts every now and then, not so much this year, but you can either try to bring more water in to fuel the machine, or you can try to find ways to reduce what you're using today. And that's kind of what we're doing with LED. We're trying to find a way to reduce the manufacturing footprint of what it is you're producing today and produce it more efficiently. Another area that really is impacting all businesses is safety, sustainability, and all of this leads to greater uptime. So workplace safety matters to every single manufacturing company around. Lawsuits are very expensive, and companies genuinely do care, I think, for the most part, about the safety of their employees. Big brands are also asking, what are you doing to be more sustainable? How is your production process becoming more sustainable? Brands like Procter & Gamble and the Walmarts and folks like that are demanding their suppliers to find ways to become more sustainable. LED answers that question. The other big area here is uptime, with reducing your maintenance that's typically required with various alternative curing systems. With the instant on-off nature of a solid-state electronic device, your uptime is going to be greater than it was before. And uptime all leads to throughput, good quality product, and ultimately money. So on to a couple examples. I've got 4 examples. First one from the industrial coating segment. The dark spot in this production process was that the thermal bake process took 1 hour to dry and fully adhere this coating. The steps after that bake process were the cool down. So it was a 2-hour cool down period. And this warehouse was filled with all these metal parts, fans oscillating in the warehouse and everything, just trying to cool racks and racks and racks of this finished product. Well, the biggest challenge was, this is a coating and it's LED. What about surface cure? How are we going to cure the surface? The wavelength is all wrong. But when these challenges present themselves, it's really about the process. It's trying to bring everybody to the table. The machine manufacturer, coating supplier plays a huge, huge role in the performance of an LED curable coating, as well as the LED lamp supplier and the end user themselves. When all parties are working together, that typically is going to lead to determining what are the right curing conditions, and let's prove it out with a trial. So the outcome, the first system's up installed, running very well. There's several more that are expected to be installed this year. Overall ROI is going to be less than a year for each one of these systems. The number of units that they have sitting in work in process has drastically reduced. And the energy and space savings were all a real major plus for this outfit. They were actually paying trucks to sit in their parking lot while they were waiting to pick up the finished goods, because they were still going through the final cooling process to then be palleted and shipped out the door. So really have had some savings come from various different angles, and even more to come in this industrial coating project. So flexo printing, the dark spot here, it kind of applies to a lot of different businesses. They were maxed out at their power draw for this particular facility. In the municipality, they were one of the highest consumers of electricity. They were dealing with all kinds of red tape and a significant cost of over $100,000 it would have cost to bring more power into this particular facility. So the biggest concern here is it going to work? What about LED? I've heard about it for years, so forth. Well, the way to really determine whether it works is to prove it out. Working with the ink company, running trials on press is what really grew confidence that, okay, this is still UV curing. My inks really aren't that different than they used to be. And then it made the transition to a UV LED process seem a lot less daunting than it was out of the gate. So as it turns out, the energy draw on the new system was significantly less than was originally anticipated. And a lot of this has to do with uptime, with the amount of time the press is actually running, producing product, versus sitting in an idle state. The LEDs are going to be instant on-off, only on when the press is running. The other ancillary benefits that came from it was reducing all of the infrastructure related to the exhaust system. Not only does it look a lot cleaner, but those exhaust systems are also pulling air from the production environment. And in the winter, that's heated air that's going out the ceiling, and in the summer, it's conditioned air, which is all being pushed outside of the manufacturing facility. So that has an impact on the efficiency of the HVAC system, which all relates to the energy draw. So by replacing the existing curing system with the UV LED curing system, all of a sudden their energy consumption started to go down. The more systems that they add, the greater the benefit becomes. How about composites? This is an awesome area, an area that UV has kind of dabbled in and been interested in for quite some time. As it turns out, the wavelength, the high UVA wavelength of UV LED tends to work really well curing composites. So the dark spot in this process was that it was a really long, slow bake process. It was very hot, using lots of energy, and the equipment was just really dated and needed significant repairs or upgrades. The performance property of the composite itself, too, is kind of losing a little bit of luster. But the challenge here is LED even going to work curing this opaque, kind of thick resin? And after working closely with the chemistry supplier and tweaking the formula to optimize it for the wavelength that was emitted, it turns out things started to work really well. And once some positive feedback was coming from the lab, that really got the attention of top management. They started to wrap their head around the idea that we don't need these big ovens anymore. We can actually get away with a system that is a fraction of the size of the one that we have in place. So one of the unexpected benefits was that the composite actually started to perform 40% better than the original version. So all of a sudden, this started to really become a reality for these folks. And to get a product that's going to outperform the old product and be a more efficient manufacturing process really does check quite a number of boxes there. So there are some other limiting factors in the speed at which you can pultrude and some steps of that process, but the UV LED curing portion is not going to be a limiting factor as they move forward. So for the fourth example, this kind of falls into the adhesive area. This is a potting compound. The dark spot in this process was that the potting compound just wasn't really performing as well as it had been historically. And the company had been considering LED for quite some time. It's an automotive part, so that adds some layer of challenge when it comes to meeting the automotive test standards. In this situation, you're going from UV microwave to UV LED. The bulk of the formula remains the same. Some tweaking of some photoinitiators and things like that are really what was required in order to optimize the performance of the potting compound. The process, again, was collaboration with all the parties involved, including the adhesive supplier and the end user, to figure out what is going to be the optimal arrangement of the UV LED light sources to get consistent exposure over this automotive part that had various peaks and valleys. This picture is an example of an automotive part. This isn't the actual part itself. But these optical renderings, which are the picture in the middle and on the left, at first we thought it would require 3 light sources to shine on an angle and then 1 in the middle to illuminate the whole part. But as it turns out, 1 light source with a reflector did actually a better job of consistently spreading out the energy across the entire part. So fewer lamps were required, a slightly smaller footprint, and a simple reflector turned out to be the optimal design for this system. So the size of the LED equipment fit very nicely within the existing footprint where the microwave lamps were. The workplace safety was improved on account of no UVC or UVB wavelength energy. And overall, the system was a lot lighter, a lot more reliable. It didn't require as much maintenance, and nor did it produce as much heat as the previous system. So with that, we'll talk a little bit about sustainability. Historically, we'd always said 50% energy savings was what you can expect comparing a traditional UV system to UV LED. As it turns out, it's a lot more than that. It tends to be closer to 70%, if not more, in some situations. And another big factor in all this is really just reducing the tonnage of CO2 that is coming out of the facility. So as a company, we try to work with customers and try to better understand what those savings may look like for their operation. Here's a cool graphic that'll play here related to bulbs. A mercury bulb's not that expensive on the surface, but once you start adding up the number of replacement bulbs over the lifetime of an LED system, it can really start to add up to become a material number that can affect bottom line. And it's also about the waste. A lot of these probably end up in dumpsters. We'd like to think most people are responsibly disposing of mercury bulbs, but the reality is that's probably not the case for everybody. So anything we can do to chip away at that is going to be a net positive for all of us. And at 70% energy savings, a typical 8-station flexo press, 20 cents per kilowatt hour, removal of the exhaust and things like that, it can add up to about $50,000 per year. So these are real numbers that matter and that can certainly impact bottom line. One thing that doesn't often get talked about is the LED light source itself is recyclable, just like your cell phone or your computer. You can't take our lamps to Best Buy and drop them off, but you can send them back to Phozion. Our manufacturing facility is outside of Portland, Oregon, and we will take units back and take them apart, the PCBAs, the aluminum, steel, separate all the metals and recycle them responsibly. We're also working on how do we do this regionally in different parts of the country and certainly different parts of the world. The units will not last forever. They're going to last a very long time, but when you do reach the end of that life, we want to make sure that we kind of think of this cradle to grave and make sure that those LED units themselves are being recycled responsibly. So what questions should you be asking your customer base and to try and better understand whether or not LED could be of value to them? Well, just better understanding what the bottlenecks are of their process is a really good place to start. And what are the true maintenance costs associated with a particular production line? The downtime associated with maintenance, with warm up and cool down, and also rework of product that was not cured correctly the first time, all factors into the real total maintenance cost. A lot of times these costs fall into different buckets. They come out of different budgets and aren't always in front of the decision makers for the companies. So we always want to try and bring these questions up with folks to make sure that they're considering all the costs that are associated with their existing system. In many places, there's a person who is responsible for maintaining the mercury units. It's their go-to, it's their trade, it's what they do every single day. Well, if that person weren't maintaining mercury systems, that person really could be deployed doing something more productive for the operation. And what about future regulatory drivers? We know that mercury is sort of in the process of being banned at various different levels in Europe, and it'll spread to the rest of the world. Eventually this will happen, we don't know when, but the mindset has to be, when this day does come, am I prepared for it? And if not, what can I do to better prepare myself for future regulatory pressures against mercury? When was the last time you considered LED? Some people haven't looked at it in 2, 3, 4, 5 years even. And a lot has changed. The landscape has changed. What a lot of you folks have been able to do is been able to advance the chemistry. We just heard a talk about photoinitiators, more potential photoinitiators that can be used to work well with high UVA. This is an evolving market. It's always changing. And if somebody considered LED more than 2 years ago, they should absolutely be considering it again to see what may have changed in their favor. Also, LED is not all for nothing. You don't have to have all LED or no LED. You can start with 1 or 2 systems to solve one particular production problem and then eventually adopt more over time. So it's really important that the barrier to entry is very low. Even just a lab unit could go a long way in better understanding how does this future technology affect what I'm trying to do today. And who are your most strategic suppliers? Are they really the ones that are adding value, that are the ones that are helping you advance your manufacturing process? Always have to consider everyone that's out there. Here's another really awesome thing we've got going on. States have money that they will give manufacturing companies to invest in making their process more sustainable, lower energy, and so forth. The same types of credits that have gotten everybody to change their light bulbs to LED exist, and the return could be even bigger in a manufacturing process. The challenge is, how do I figure it out? If anyone's tried to get state subsidies or township subsidies to offset the cost of a hot water heater or windows or a roof to make your house more efficient, it's a daunting task. It's not that easy, and it can be very, you can just lose interest pretty quickly. Well, I've gotten to know this Titan Energy, who is a consultant firm out of Connecticut, who works with end users to first identify what are some of the biggest energy draw parts of their manufacturing process. This is both electricity as well as natural gas, and they're able to put a package together and submit it to the local governments and the state governments in their particular state to apply for tax credits, to apply for subsidies to offset the cost of investing in an LED curing system. They've had some really great success, and they're a very nice company to work for. There's no upfront cost or anything associated with it. They do end up getting a fee based on whatever the savings are for the company, but it ends up being a win-win. So I wanted to mention it here because I think it's important to leverage consultants, firms like this, and many of them exist. These folks can work in all 50 states, and we'd be happy to talk more about this if it's of interest to anyone in particular. So with that, I appreciate your time, and I'm happy to take any questions that you may have.
Anybody have any questions?
Mike, for your example 3, how thick the composite material you can cure? Or ever try? You mentioned what is opaque, right? It's opaque.
Mm-hmm.
But how thick you can really glue through?
Yeah, that's a good question. I don't know the measurement of how thick it actually is, but I do know it's a lot thicker than a typical laydown of ink or a coating. You can find out more details, though, if you're interested in that area. Yes?
In the example for the coatings on metal, is that in one pass to cure, or is that like a primer going over?
Yeah, so it is a single pass. There are multiple LED units that are used to give full exposure and maximum energy density to cure that coating. So it is, I would say, hit with 2 lamps back to back in order to give an appropriate amount of energy to get the surface cure. And that is not done under nitrogen.
You mentioned that a lot has changed in the last 2 years, and you mentioned photo initiatives. Have you seen changes on the component side, the LED component side as well?
Do you mean from a LED lamp perspective?
Yes, the actual components.
Yeah, so during the supply chain challenges, we certainly identified a lot more components to use to build our units themselves. From that perspective, the diodes themselves have not evolved that much in the last couple of years. 395 nanometer wavelength, 365, 385, whatever, high UVA, is about 50% efficiency. So 50% of the energy going in is being turned into UV LED energy and coming out of the unit. That hasn't had any major incremental improvements like it had in years past. But what has improved would be the fans themselves that are used in air-cooled units. They've become more efficient. Some of the circuit boards that we use are getting smaller and are also getting more efficient, which reduces total heat load into the system. So I would say the ancillary components outside of the diode itself are the ones that have made incremental improvements in the last couple of years. Mm-hmm.
Right. Just a quick follow-up question about the example. Is that I know you just mentioned you use multiple lamps, but it's all 100% LED lamps, so we have to use the mercury lamp for surface.
Yeah, that's a great question. I meant to mention that. It is 100% LED. There is no mercury lamp being used downstream.
What wavelength of LEDs do you supply? Is there any invisible spectrum? Both visible, like 438, 425?
So our standard would be 395 nanometers. We also have 365, 385, and 405 as far as standard offerings go. However, we have built systems in the visible range, 420, 550. So we're willing and able to build custom wavelengths as long as those diodes exist. Yeah.
Simple question. Is there no wavelength LEDs such as UVC, UV?
Any developments in the UVB, UVC area? Well, we're really hoping Excelitas knows something more about UVC because UVC is frustrating. There's just, it comes down to availability of diodes. And those diodes have to be efficient enough to withstand the current that we're pushing through them so that the energy that comes out of the diode is enough to impact curing. What where we're at is around 2 watts per centimeter squared with 278 nanometers. That's in a water-cooled system. And if that is used in combination with UVA, with 395 for instance, 2 lamps that are next to one another, then you can create a curing environment that has both UVA and UVC, and we suspect that could help with some surface cure challenges. But in all seriousness, the partnership now with Excelitas, we're both really hopeful that putting everybody in the room together when it comes to UVC may help us move that wavelength forward, because we recognize that there is demand and interest for it in the field.
Hey Mike, what's your biggest challenge for end users when you tell the storage to switch from mercury to LED? I mean, what do you think? It's a great story. But it's not happening faster.
It probably comes down to just confidence. Change is really difficult. People typically need to show me 5 other people that are doing this, doing it successfully, then I'll change. They're generally kind of hesitant to be first movers. And conversely, the ones that have been most successful don't talk about it. None of these pictures or images I put up here are the product. I'm just throwing you guys off. They're different, but the stories are all consistent. So the ones that tend to be the most innovative are the ones that tend to also keep things close to the chest. I think what ultimately drives people to change is cost, is regulatory pressure, right? People have to be forced to change, and we're kind of getting there, it seems, eventually. So I think it's a variety of different things that drive that.
Yeah, one additional comment I'll make just on, we often, evolution of electronics are often correlate very closely with Moore's law, right? So when you think of microprocessors and electronics, things get astronomically better with each passing year. UV LEDs, while they were electronics, we still have to follow the laws of thermodynamics. So energy conversion is only going to happen at the rate that energy conversion is going to happen. So we're really at the point with LED technology where we're kind of where we're at. We're going to be there for a while. Shorter wavelengths are all material science, and in terms of getting more energy out, we're kind of limited by the physics of thermodynamics. So what we need to rely on is continued collaboration with the industry to get chemistry and the projects aligned.
And to that end, saying that fans have gotten better, doesn't sound cool, but that matters. I mean, if the fans are more efficient and we're able to push more air through a heat sink, that means we can drive that diode a little bit more. And now all of a sudden you go from 20 watts to 24 watts per centimeter squared, and that might be that threshold to cross in order to gain curing properties.
If somebody, did you ever do this, calculation? Someone's got a, just a standard medium pressure mercury arc lamp system, and they're really only after 395, but they gotta make all this UVA, whatever. How much less heat would a sensitive substrate see with a UV, with a diode system? I don't know if you ever done anything like that. Just give me a rough.
Yeah, it's orders of magnitude less. And there's a couple factors there. There's the heat is one aspect. The LED unit can be dialed anywhere from 10% to 100% power. So you can dial it back to match the line speed that you're running. But the wavelength is initiating the reaction, of course. A lot of the distortion of substrates tends to come from shrinkage, from those molecules grabbing on so tightly to one another. The fact that 395 isn't perfectly aligned with the photoinitiator actually kind of reduces that shrinkage a bit, which has an impact on how substrates are affected by those wavelengths.